This diagram's on contractility. This is huge. I'm going to put a star by it, a couple stars by it. Contractility is heavily tested, okay, because not only is this a physiology thing, but this is major in treating problems with the heart. So as you can see here, what's different here? So we got our flow volume loop, our pressure volume loop, and so what has happened is you can see that this point right here has changed for our three situations, okay? And so afterload has not changed. You can see there that the ejection starts at the same point, but what has changed is contractility. And so what is contractility? I wrote it right here, dP divided by dt. You could also write delta P divided by delta T, so it's the change in pressure divided by the change in time. So if pressure is going up faster than time, then you have an increase in contractility. You know, it's that that actual contraction. You know, it's harder. The heart is beating faster and more forcefully. So and I should also say there's one counterintuitive thing about this is that not only is it beating faster, it's actually relaxing faster too. Sometimes questions ask about that and people get tricked. So anyway, but the peak isovolumic pressure. So remember, PIP is a big deal, and the reason why is because the peak isovolumic pressure is determined by contractility. So there's a line here, and you can change everything, every other variable you want. You'll always end your systolic volume here. Your ejection will happen and it'll end here on this line until you change contractility, and then the line shifts. So going up this way, we had an increase in contractility, and then going up again, we had another increase in contractility. If the line went down, and I didn't have that drawn in here, that would be a decrease in contractility. And actually, I should have drawn that in there because this would be a really good example of heart failure, because there's less contractility in heart failure because maybe some of the heart muscle died or something like that. So anyway, so let's take a look at this. Okay, so we're filling the heart once again. So as we're filling the heart, we're going this way on the volume curve. And so we're passively filling the heart up until we get to this point here, which is called preload. I tricked you that time because I've been calling it end diastolic volume. So you could also call it LVEDV. Okay, what would I be saying then? Left ventricle end diastolic volume. Okay, or you can also say end diastolic pressure. Okay, so this is all passive to this point. At this point, we start contracting and we have isovolumic contraction. We get to afterload, we open the aortic valve, ejection happens, and so like in this blue, kind of standard one that we have, ejection happens to here, right to that point there. Peak isovolumic pressure. We're at the peak, we're isovolumic, and the pressure is here. Okay, peak isovolumic pressure. And then there's a line that goes like that. So okay, so we increase contractility. We can do that a lot of ways. There's sympathetics. The sympathetic nervous system increases contractility by increasing calcium concentration. So remember these brackets mean concentration. We talked about the medication cardiac glycoside, which is a class of drugs in which the one that's used the most is digoxin. And what that does is it blocks that potassium channel, which causes sodium to be retained within the heart, which means that calcium is retained within the heart. So, so calcium equals contractility. The more calcium concentration that you have in the heart cell, the harder it's going to contract. The calcium is what makes the actin and myosin interact. So the more calcium, the more interaction between the actin and myosin, the harder and more forceful the contraction. Okay, so this gray line here that we got going right here, so we increase contractility, and we can tell that it's increased because, boom, we ended right there. It's a different peak isovolumic pressure line than what we started with. Okay, so we give the patient a little bit more digoxin or cardiac glycoside, and contractility increases again. Now we're at this next one, and you can tell that contractility increases because we ended on a different peak isovolumic pressure line. So you can see that here, that the line once again has shifted up. So so I've got some things here, and there's a lot of things that can increase contractility, and so take a look at these four. So calcium, like I said, that is the definition of increasing contractility. Sympathetics, that also increases contractility. Heart rate increases contractility. There's more residual calcium as the heart is speeding up. There's more calcium that does not go out of the cardiac myocyte, so there's more calcium in there, so the contractility increases. One that you wouldn't expect, and I kind of doubt you'll get tested on this, but afterload also increases contractility. Um, the causes are, or what an increased contractility causes, it causes an increased stroke volume, it causes an increased ejection fraction, and it causes an increased force of contraction. And those causes are just kind of by definition. Contractility causes these three things. It causes other things too, but generally just try and understand the concept. Physiology is something that should be understood and not necessarily memorized. And then the harder test questions will ask you to apply the concept to what they're asking you.